What if everything you've ever known, every object you've touched, every star in the night sky, or every cell in your body is actually made of something even smaller than atoms? What if, at the deepest level of reality, everything is made of vibrating strings of energy, each playing a different note in the grand symphony of the cosmos? This is the central idea behind string theory, a concept that attempts to unify the forces of nature and explain existence itself. So, what is string theory? For centuries, scientists have struggled to understand what reality and our universe is made of. The ancient Greeks believed everything was composed of four elements: earth, water, air, and fire. Later, as science advanced, we discovered that all matter is made of atoms, which we once thought were indivisible. As our technology advanced, our ability to probe deeper allowed us to learn that atoms are made of even smaller particles: protons, neutrons, and electrons. And inside protons and neutrons, we found quarks, tiny building blocks that seem to be the fundamental units of reality. But there was a problem. The physics that describes these tiny particles is called quantum mechanics, and it works very differently from the physics that governs massive objects like planets, stars, and galaxies. General relativity works for larger-scale physics and explains how gravity works, bending space and even time itself. Quantum mechanics and general relativity have each been remarkably successful at explaining different aspects of the universe. But when scientists try to merge them into a single theory, the equations clash. The math falls apart, producing contradictions instead of a unified understanding. For decades, physicists have searched for a theory that unites them, a so-called theory of everything. And that's where string theory comes in. String theory proposes that what we think of as tiny particles are not actually particles at all. Instead, they are tiny, vibrating strings of energy. Just as the strings on a violin can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in different ways to create the particles that make our universe. The electron is a string vibrating one way, a quark is a string vibrating another way, and so on. If this idea is correct, then everything in the universe is made of the same fundamental ingredient. The only difference is that they have different patterns of vibration. One of the most intriguing aspects of string theory is that it naturally includes gravity. In the standard model of particle physics, which describes all known particles and forces, there is no clear way to include gravity as a fundamental force. But in string theory, there would be a certain vibration of these tiny strings that results in the creation of a particle known as the graviton, the particle thought to be the carrier of gravitational force. String theory could finally unite quantum mechanics and general relativity, solving one of the greatest mysteries in physics. But if strings are real, why haven't we seen them? The answer is quite simple. Strings are so incredibly small that even our most advanced microscopes and particle accelerators wouldn't be able to detect them. Imagine this: if an atom were the size of the solar system, a string would be smaller than a tree on Earth. Because of this, testing string theory directly is extremely difficult, and some scientists criticize it for being more of a mathematical idea than a testable scientific theory. Another strange consequence of string theory is that it requires the existence of extra dimensions. For the equations of string theory to work, the universe must have at the very least 10 dimensions. But if these extra dimensions exist, why don't we see them? Scientists believe that these extra dimensions might be curled up or compactified into tiny shapes at every point in space that are again too small for us to detect. Space might contain additional dimensions that we simply can't perceive. But if string theory is true, it would completely change our understanding of reality. It suggests that space and time, which seem so fundamental, may not be fundamental at all. Instead, They could emerge from the interactions of strings in ways we don't yet understand. Some physicists even speculate that time itself may be an illusion, a side effect of deeper, hidden processes that strings are responsible for. The implications of string theory go far beyond physics. It raises questions about the nature of existence. If everything is made of vibrating strings, is the universe some kind of grand musical composition? Are we, in a sense, notes in a cosmic symphony? If the universe really is governed by these mathematical patterns, does that mean reality itself is like digital computer code? A program running on some kind of cosmic computer? Some versions of string theory suggest that our universe is just one of many, floating within a higher dimensional space like bubbles in a vast ocean. Our entire observable universe could be just one tiny region of an unimaginably vast multiverse. Some of these universes may even have different physical laws, different types of matter, or even different versions of ourselves. Despite its beauty and potential, string theory remains controversial because its predictions are so difficult to test. Some physicists argue that it may never be provable, and that science should focus on theories with clearer experimental evidence. But many believe that string theory is our best hope for understanding the deepest workings of the universe. And as technology advances, we may find indirect ways to test its predictions. String theory suggests that our universe is far more complex and mysterious than it appears, that beneath the surface of our everyday lives, there are hidden dimensions, vibrating strings, and the possibility of an endless expanse of alternate realities. Our search for truth in understanding reality may be a journey that never ends. With every new discovery, the universe becomes even more awesome than we ever imagined. We hope you enjoyed our exploration into string theory and invite you back for our next episode